Hello, my name is Nael Fasfous. I'm a PhD student at the Technical University of Munich. Together with my colleagues, we are happy to present to you BinaryCoP, our binary neural network-based COVID face mask predictor on edge devices. Here's a brief outline of the talk. First, we will go over the problem statement. Then we will talk about some common challenges for AI deployment and the lessons learned from our work on BinaryCoP. Then we will discuss how we dimensioned 3 different prototypes of BinaryCoP, and we will compare with existing work that's tackling the same problem. So face masks have been proven to be an effective solution to mitigate the spread of COVID-19. And in most public indoor spaces, there are already mandatory rules on wearing these masks. However, the problem is to guarantee the compliance with these rules, and also it's hard to assert that people are wearing the masks correctly, which is very important to their function. So our problem statement is quite straightforward. We would like to deploy accurate, unbiased image classification algorithms, which can be used at entrances or speed gates to check the correct mask wear and positioning. Again, positioning is very important to the correct function of the mask, with all processing happening on low power, cheap edge hardware. Again, for these to be placed ubiquitously in public areas, they have to be cheap and easy to deploy. And finally, we would like to have a privacy-preserving aspect where the processing happens on the edge device and nothing gets communicated to the cloud. So the challenges for a typical AI deployment can be split into 3 distinct problems. First, the collection of diverse, clean datasets so that you can guarantee that the performance that you observe during training matches that which you could expect in a real-world scenario. Second, low-power AI on edge typically requires that you offload your computing to the cloud, which is something that we would like to avoid for our particular application. And lastly, the algorithms are typically treated as black boxes, which is something that we would like to avoid. We would like to better understand why our algorithm is making certain decisions so that we can refine the training and improve our final deployment performance. In the context of our COVID face mask predictor, let's take a look at the first challenge, dataset diversity. Large-scale natural face datasets do exist, but the number of real-world face mask images is limited. Here we have a dataset that is predominantly collected in East Asia, which limits the facial features and hairstyles and skin tones of the subjects. Instead, what we could do is opt for a more diverse set of subjects and apply synthetically the masks that we would like to predict. And this way we can also vary the type or way of wearing the mask, which helps us also identify incorrectly worn masks. The question now is, should we sacrifice real-world accuracy for diversity? The answer is, we can be a little bit smarter about how we create our synthetic data. We can vary the type of mask that's applied to the subjects. We can change the mask pattern. And we can, of course, play with the color and intensity of the mask such that we have a diverse set of masks being applied to the different subjects that we have in our natural face dataset. Another thing we can optimize is the type of network that we choose to deploy. In this case, binary neural networks have been proven to have nice regularization characteristics, which might be better for them to generalize on synthetic data. And finally, we can initialize on synthetic data and then fine-tune on real-world data. So just because we're using synthetic data to train our network does not mean that we're limited to it. It's just one stage before we fine-tune on real-world data, which is a little bit more scarce and maybe less diverse. So let's take a look at binary neural networks. In these networks, we usually restrict the weights and activation values to 1 and -1. We do this with the sign function, where a latent representation of the weight can have a positive or negative value, and based on that, it's assigned either of the 2 binary values that will finally be deployed in hardware. The latent weights allow us to train, because they are still represented in full precision, while the binary weights are kept for the deployment, which allow us to have an efficient logic deployment without having full precision multipliers or fixed point multipliers. But this method of training introduces a gradient flow problem. To better understand this, let's take a look at one step of training. When we give a particular input, I, this results in output O from our network. Output O can be calculated against the label to compute a loss, and this loss can be used to update our weights in the backpropagation step. Now, backpropagation is performed with stochastic gradient descent, which applies the chain rule from the loss back to the weight that needs to be updated. And every operation that happens between the loss and the weight is involved in this chain rule, right? And what we would like to do is to update W to minimize L, basically finding the minimization slope. Now, The sign function in a binary neural network is such an intermediate operation. It is inserted in the middle between the loss and the weight. If we take a look at the sign function, it looks a little like this, how we see on the bottom left, and its derivative is the delta impulse function. Now, the derivative is simply 0 almost everywhere, which, as you can see, introduces a 0 in our chain rule, which means that the gradient is not able to flow and the weights do not get updated. Therefore, the discreteness of binarization is fundamentally incompatible with gradient descent optimization. One solution to this problem is to approximate the derivative of the sign function with another function. In this case, we can replace the sign function in backpropagation with another one, in this case h tan h. And if we take a look at the derivative of h tan h, we see here that it is indeed the straight-through estimator, which allows the gradients to flow without any problems. So what do we get in exchange for this complex training scheme? High-precision networks typically have lots of multiplications, accumulation, and Batchnow operations, which are difficult to execute on edge devices, and we have wide operands that are 16 or 32 bits wide. In the binary domain, multiplications can be replaced with inexpensive XNOR operations, accumulation can be replaced with pop count, batch norm can be replaced with a comparator, and our 32-bit wide operands are now only 1 bit, which heavily reduces the memory requirements on our edge device. And as a bonus, the approximate aspect of training BNNs, remember replacing the sign with the h tan h, makes it harder to overfit on training data. This makes them a good candidate for training on synthetic data, since it's harder for them to latch onto specific artifacts that emerge from the synthetic generation of the data. Now, let's take a look at algorithm explainability. In this case, we feed our convolution neural network with a particular input image, for which we get a corresponding output, in this case, the correctly worn mask class. We can compute the derivative of the prediction with respect to the activations of our intermediate conv layer, which gives us the neuron importance weight. With these alphas, we can scale the output feature maps, aggregate them, activate and upsample them, and apply them back onto the input image to understand where that layer was focusing with respect to that decision. This way, the neural network does not need to be a black box, and we can better understand the decisions that it makes as well as its learning patterns. The last piece of the puzzle is the hardware accelerator. In this case, we choose the Fin framework, which is a state-of-the-art binary neural network accelerator. And Fin exploits the fact that BNNs have a very small memory footprint, and it uses this fact to preload the accelerator with all the weights, and then streams the input through a data flow style architecture, where we have these sequentially placed MVTU computation units, which can be parameterized for different processing element sizes and SIMD lanes. With this, the designer has the ability to parameterize the MVTUs such that there is some throughput matching happening throughout this data flow architecture, and that you are getting the frame rate that you would like to have for your particular application. Now let's take a look at the 3 BinaryCoP prototypes that we have tested. First, we have the CNV architecture, which is directly inspired by the Fin paper. The CNV architecture resembles the VGG network, which is a classical convolution neural network. Here, the CNV plays the role of having high accuracy, as it has the most number of channels and layers. Then we have nanoconv, here represented with nconv. We see that it has the exact same number of layers as conv, but having much less channels. And then lastly, we have microconv, which has low logic. We can see here we have a reduced number of layers. And for this particular network, we used a technique where we offloaded some of the XNOR operations to the DSPs of the FPGA. Let's consider the throughput matching aspect of the Fin architecture. In this case, we take BinaryCoP and conv as an example. We see that the earlier parts of the neural network require more operations to be executed than the last layers. We also know that the last layers require more on-chip memory to store their large number of parameters. This is due to the fact that we are working with a data flow architecture which preloads the weights and streams the activations through the hardware computation graph. We can exploit this information to assign more processing elements to the earlier parts of the architecture, thereby reducing the latency required for the large number of operations. On the other hand, we can reduce the number of processing elements assigned for the last layers, as they have fewer ops anyways. Another advantage here is that the fewer PEs in the last layers lead to less fragmented memory allocation by the synthesis tool, which is important for the large weight tensors of the FC layers. We can see that overall, the throughput of the accelerator is not sacrificed, as the latency of the first and last layers is roughly the same, meaning that the fewer PEs at the tail end do not lead to any throughput bottlenecks. Here we have the hard results of our 3 prototypes. We can see that the conv architecture is indeed the one with the highest accuracy, although it requires a lot of BRAM resources and lookup tables. Next, we have the nanoconv architecture, which achieves our goal of reducing memory requirements of the design while increasing the throughput. Finally, we have the microconv architecture, which reduces the amount of lookup tables required by reducing the number of layers and PEs, as well as offloading some of the XNOR operations to DSP blocks. With this architecture, we can synthesize BinaryCoP on even the heavily constrained Z7010 FPGA. It's important to note that all 3 architectures require a small amount of power when idle. This is mostly needed by the ARM architecture on the Z7020, which we tested on the Pink board. Now let's take a look at the task performance of BinaryCoP. Here we have a confusion matrix showing the classification performance of the BNN. We can see that BinaryCoP does not mistake the nose plus mouth uncovered class with the correctly masked class or vice versa. BinaryCoP makes slightly more errors between the nose uncovered class and the correct class. However, this still happens less than 1% of the time. Finally, the chin uncovered class is the class which is most often mistaken for a correctly worn mask. This is due to the input image resolution being low and the chin area being too small to detect. This could be improved in the next iterations by increasing the input resolution. Next, we have the GradCam interpretability results. Here we're looking at examples where all networks perform correct predictions. On the top left table, we have heat maps of the conv22 layers focus with respect to the correctly worn mask class. We compare 2 variants of BinaryCoP with a full precision CNV CNN, here referred to as FP32. We can see that BinaryCoP focuses on the nose area and the upper rim of the mask to make its prediction. The FP32 network is harder to interpret as it's focusing on different patches of the image. On the top right table, we have classifications of the nose uncovered class. Here again, BinaryCoP focuses on the nose and upper rim of the mask to make its prediction, while the FP32 network is focused slightly on unrelated regions, particularly for the lady in the 3rd row. On the bottom left, we have classifications of the nose plus mouth uncovered class. Here we see that all 3 networks tend to distribute the focus onto various parts of the exposed face to make their prediction. Finally, on the bottom right table, we have the chin exposed class. Here we highlight that binary variants have some degree of focus on the chin and lower area of the image, while the FP32 network is almost exclusively looking at higher regions of the face. We further validate BinaryCoP's performance on different age groups, hair and headgear, as well as heavily manipulated faces, such as wearing double masks or painted faces. We can see that BinaryCoP is indifferent to these aspects as it keeps focusing on the same features mentioned in the previous slide. Interestingly, the FP32 CNN seems to often focus on unrelated regions, here marked in red. Now let's take a look at a demo of BinaryCoP. First, we start with a high performance evaluation. Here, a fast video is being classified without any frames being skipped. Next, we have a low power demo. Here, the accelerator classifies images from a live camera input. We are certainly not the first to tackle this problem. Here we have 4 other works that took different approaches to solve the task. It's important to note that it's hard to compare with other works due to the high degree of variation in how the task is being addressed. NVIDIA's approach targets high-resolution images and an object localization CNN to detect the location of the subject wearing the mask. Here, only a mask or no mask classification is being made without consideration to how the mask is being exactly worn. Overall, it is a more complex task which executes on expensive hardware, making it hard to apply ubiquitously in public areas. Amazon more generally classifies many types of protective gear being worn by the subject. However, their approach involves cloud processing. Wang et al. Develops a serverless in-browser processing technique. However, this requires a WebAssembly browser, which is typically more expensive and inefficient on cheap embedded devices. Finally, the Check Your Mask app informs the user about their mask by taking a selfie. Here again, the app is designed to run on standard Android devices where low power and continuous surveillance is not the target of the application. BinaryCoP presents itself as an interesting alternative that adds to these existing works and tackles the problem using BNNs, synthetic data, and low-power FPGA design. In conclusion, with BinaryCoP, we try to tackle the common AI deployment problems mentioned at the start of this talk. We kept our data diverse by opting to train on synthetically applied masks on a diverse dataset of natural images. To maintain privacy and security, we avoided cloud computation by opting for a BNN-based classification on edge devices. Finally, we tried to understand the BNN's learning behavior on synthetic data by applying interpretability techniques, allowing us to assert that the correct features are being learned. Stay safe, and thank you for listening.